Assalamu alaikum wa rahmatullahi wa barakatuh. Today, our last topic actually in this course, we will discuss about applications of stability and kinetics, concept application of stability and kinetics. The aims of this lecture that at the end of the session, you should be able to describe factors affecting rate of reaction, know the kinetics of drug decomposition, know the accelerated stability and stress testing, understand the concept of Q10 for estimation of shelf life, describe the physical possibilities, describe the packaging and stability of drug products, understand the instability possibilities in different formulations. First, we start with defining what is drug stability. To say the drug is stable means it can retain the characteristics that it had at the time of manufacturing. There may be some changes, but they should be but these changes should be limited and within acceptable limits. Okay, so USP, the United States Pharmacopoeia, defines, this is a standard definition of stability, defines the stability of pharmaceutical product as the extent to which a product retains within specified limits and throughout its period of storage and use the same properties and characteristics that it possessed at the time of its manufacturing. Okay? So as we know, let's take tablet as example. For tablets, we may need to do some tests like hardness, friability, dissolution, and so on. Let's look at the assay, for example. The acceptable limit may be that the tablet assay result is between 110 and 90%. So at the time we produce the medication, maybe the concentration is 100%. The acceptable limit is only up to 90%. So during the storage period, the drug may lose 10% of its assay. This is acceptable limit. Okay, this is a specified limit here for assay. So the period of time where the drug assay decline only by 10%, or we can say reach 90% and not less than 90%, we call this time period a shelf life. Okay, shelf life is here the time between production date and expiry date. Okay, so if we determine that the drug will take about, say, 3 years for the assay to decline to 90%, and we consider this as the shelf life, then if a drug is produced in January 2024, then the expiry date should be how long? 3 years means it should expire in January 27. Okay, this is the drug stability, the extent to which a product will retain within specified limits and throughout its period of storage and use the same properties and characteristics that it possessed at the time of its manufacturing, or at the time of its manufacture. Okay, or at the time of its manufacture also, you can say, can be correct. Okay, so this explanation is about the drug to be stable during the storage. How about during use? This one means that, for example, if we open the container, for how long it can be used, because maybe a syrup bottle have a shelf life of 3 years, but this is when the bottle is closed and stored. But once you open the bottle and you start use, then we have different instructions for the period of use. Okay, we will mention later on. Okay, why do we need to do stability studies, and why we need to inform why do we need to study stability? Because it will provide evidence on how the quality of a drug substance or drug product varies with time under the influence of a variety of environmental factors such as temperature, humidity, and light. Based on this, we can recommend the suitable storage conditions where the drug will remain stable. Storage conditions here, we can recommend the appropriate temperature for storage, the appropriate humidity, and the duration. The duration of storage, or what we call it shelf life. After this period, the drug cannot be used anymore. If you store on higher temperature, at higher temperature, they cannot be used because it will degrade quickly. Humidity, same thing. Okay. Stability studies is done to establish a retest period for the drug substance or a shelf life for the drug product and recommended storage conditions, as I explained. For drug product, I explained already what is the shelf life and storage condition. For drug substance, when I say drug substance, I mean the raw material. So you may have, for example, paracetamol tablets. This is a drug product. But if you say paracetamol, the API, the active pharmaceutical ingredient, or the drug substance, this is a pure paracetamol, no excipients added. It's not tablet, not syrup, not anything else. It's just the paracetamol. We have to know the retest period. We have to identify the retest period. What is the retest period? It's something like shelf life. In a pharmaceutical company, they receive raw material. They may use some of it for production of certain batches, and then it may be the remaining will be stored for some time. Later on, I may use for production of other batches. So, for how long it can stay on the shelf in the store and can be used for production, I should have a stability study and know the time the concentration will go down to critical values, that by this time I have to retest it again before I decide to use in other batches. Okay. Okay, so during stability studies, if I want the drug to be stable, I want it to have the characteristics we said that it has during, it keep the characteristics it has during manufacture. So what characteristics I look for? I look for physical, chemical, and microbiological characteristics of the product. Okay. I need that these characteristics should be stable during the shelf life so that the drug may be still effective and still safe to be used. So stability studies, as I explained in the previous slide, can be done for drug substances and can be done and also done for drug products. What is drug substance? As I told you, this is the unformulated drug substance. The most common term used now is we call it API, active pharmaceutical ingredients. Active pharmaceutical ingredient. Okay. This is the raw material, the drug substance in its raw form. It's not formulated as dosage form. Okay. This one I will subsequently formulate by addition of excipients to make a dosage form. This dosage form, we call it drug product. Drug product is the dosage form in the final immediate packaging intended for marketing, controlled and documented determination of acceptable changes of drug substance or drug product need to be identified. Okay, so during stability studies, I need to document the acceptable changes of the drug substance or drug product during storage. So these are the types of stability or characteristics I need the drug to have these characteristics stable so that it will remain safe and effective. Number one, I need chemical stability. Chemical stability means that the active ingredient retains its chemical integrity and labeled potency within the specified limits. What is labeled potency? You may have a drug, for example, the name is, say, paracetamol tablet. Paracetamol 500 milligram tablet. Okay, so this is the labeled potency. One tablet contains 500 milligram. When I say, when I talk about chemical stability, means I want this amount of paracetamol in the tablet to be stable during the shelf life, will not decrease by big amount, but if decrease within specific limits, not more than 10% decay. Okay, in some drugs, even the allowed decrease is only 5% from the labeled potency. Labeled potency is the one on the label. You have the package of the product, and then it is written, for example, paracetamol 500 mg. This is the labeled potency. Or we call it, in other words, strength, right? Strength of the dosage form. Physical stability, I want the original physical properties, including appearance. The color doesn't change. Palatability, the taste doesn't change. Uniformity, okay? Uniformity of the shape, the dose, dosage, the weight, uniformity of weight. I want the dissolution to stay the same. The ability of active ingredient to dissolve once you put in the solution. Medium is the same, so that means it can be absorbed. For example, you take tablets must disintegrate and dissolve, the active ingredient dissolve first before it can be absorbed and reach to the blood. So I need the dissolution ability of the active ingredient in this dosage form to remain same, okay? And then suspendability, for example, if you talk about suspensions, I want suspendability to be same. I don't want to have a cake at the bottom of the bottle that whatever you shake, the drug will not be suspended again. This means that difficult to administer accurate dose of drug. Okay, microbiological stability means I don't have any abnormal growth of microorganisms. The content of microorganisms is the same, doesn't change. For example, you have a sterile dosage form, like injections. It should be sterile, means zero microbes, zero microorganisms in this dosage form. So it should be sterile upon production and remain sterile during the shelf life. You have some dosage forms that are non-sterile, like tablets, ointments, capsules, okay? For them, we make another test we call microbial count. We call this test microbial count. Each test sample is allowed to give a certain number of colonies in the Petri dish once I do the culture in the lab, in the microbiology lab. So at storage, with storage, I don't want also this microbial count or content to increase or change, okay? Not only the microbial tests, but also if they have preservatives, then I need the antimicrobial agent or the preservative to remain effective during the period of storage. So when I determine the shelf life, it's not only about the content of active ingredient, but it's also about the content of preservatives. The concentration of preservative should not go down below the minimum inhibitory concentration. Okay, otherwise, because it's also, the preservative is also a chemical ingredient, and this chemical ingredient also may have some degradation with time upon storage. So if it reaches below the MIC, then it will not prevent the growth of microorganisms anymore, and then your product will have microbial growth. So this is not suitable for consumption anymore like this. All of this is aimed at having chemical stability and physical stability is aimed to, and even microbiological stability is aimed to keep or to preserve therapeutic and toxicological stability of the product. Therapeutic stability means the therapeutic effect remains unchanged. Okay, the therapeutic the therapeutic effect of medication doesn't decrease if it still can perform well physically, and then the content of active ingredient is also the same. then it will supposed to give the same therapeutic effect. When it comes to toxicological stability, this one is about therapeutic stability is about efficacy. When you talk about toxicological stability, this is about the safety. I don't want significant degradation that will give high amount of degradation products that may be toxic. Okay, so during storage should have no significant increase in toxicity, and this toxicity also may be due to microbial growth, right? So I don't want microbial growth. I don't want also formation of toxic degradation products with harmful amounts. So in this case, I will preserve the toxicological stability of my product. Okay. This part actually is the remaining slides from the previous lecture. So, but here is discussed with with more details. So this should be replaced the part that we didn't discuss last time. First, we explain about examples of physical instability. Physical instability examples like crystal formation in pharmaceutical preparations. For example, for some drugs like chloramphenicol, they may be available in different crystal forms. They can be present as amorphous and can be present in crystalline form. So changing from one crystalline form to another is considered physical instability. And you may ask, so what? What's the problem if there is a change in the crystalline form or change from amorphous to crystalline? Because change in crystalline form will lead to change in the physical characteristics, like, for example, dissolution, like solubility, melting point. Several physical characteristics are different. For example, here, the most important for me is the dissolution. So it may change from a form that will dissolve easily in the GIT and can be absorbed to a form that have solubility problem. So this will affect the bioavailability of the drug. Bioavailability here means the amount that will reach to the systemic circulation. So the drug effect will be affected. The drug effect will be decreased because less amount can reach to the circulation, right? Second is, for example, if you prepare a saturated solution and then you know that solubility is affected by the temperature. So you prepare the saturated solution at certain temperature, and then there is a temperature change, for example, reduction in temperature, then some of the drug may precipitate, and then you have undissolved amount of the drug in your dosage form. This is a kind of physical instability. In suspension also, there is a phenomena called Oswald ripening. This is a very common, can happen in suspensions, can also happen as well in emulsions. Okay, so Oswald ripening can also happen in emulsions, not only in suspensions. So what happens in this one? You prepare a suspension or emulsion that give you some range of particle size, say, for example, from 20 to 200, say, micron, the particle size. Okay? In Ostwald ripening, these small particles will dissolve and will be added to the larger particles. The larger particles will grow. So small particles in suspension disappear, and large particles grow after repeated temperature changes in both directions during storage. In both directions, maybe temperature is changing up and down. Okay. In emulsion, it also happened due to solubility of the emulsified phase or the oil phase, for example, if this oil water emulsion in the aqueous phase, then it will combine with the big particles. So these big particles will grow, their size will increase more than 200. So if you keep your emulsion or suspension, you measure the particle size upon manufacture, you find it within the range 220 to 200, for example. Then after 3 months, you measure again, you see that the range may be changed to for example, 100 to 280. After a few months, maybe increase more and more. So this is considered a kind of physical instability. Another type of physical stability is the loss of volatile substances from pharmaceutical dosage forms, and these are examples of pharmaceutical dosage forms that contain volatile substances. Aromatic waters contains aromatic substances that are by nature are volatile. They are dissolved in water, so they may evaporate. Elixirs containing mixture of water and alcohol. So this alcohol may evaporate. And the drug is dissolved in this solvent. The solvent is water alcohol mixture, and there are drugs dissolved in this one, in this solvent. So the solvent, the alcohol itself, will precipitate, it may evaporate because it's a volatile substance. So here there will be a problem with the solubility of the drug because you added alcohol to help to dissolve the drugs that are not water soluble. If alcohol is removed by evaporation, then only water remains, which cannot dissolve the drug, and the drug will precipitate. Spirits, they contain hydroalcoholic solvent, and there is volatile substance dissolved in it. So alcohol and volatile substance may evaporate. This is a physical instability. Okay. So some tablets which contain, let's say, volatile substances. These tablets, the volatile substance may also evaporate from it. For example, nitroglycerin tablets. This is an ingredient, the nitroglycerin is used for treatment of angina pectoris. Usually can be used for emergency cases when the patient has heart attack, has chest pain. He can just place it under the tongue and then the drug will be absorbed. Nitroglycerin by nature is volatile. So with storage, especially if the container is not tightly closed, then there will be evaporation of the nitroglycerin from the tablets and the content will decrease. Okay. In some dosage forms, there will be loss of water. This is considered also another physical instability. If you have a saturated solution, if there is loss of water, which is the solvent, then what will happen? There will be precipitation of the solute because it will become super saturated. Emulsions, if there is loss of water, then you may have growth of the droplets of emulsion, or you may have the two phases separate. So instead of having oil droplets, for example, if in case of oil and water emulsions that are homogeneously distributed within the aqueous phase, then you will have separation. You will have two layers. One layer is oil and then the other layer is water. This is separation of emulsions in general is called a physical instability, whether water lost or no. Okay, so there are several factors that may cause separation of emulsions other than water loss. Creams, actually the composition is oil and water emulsion, and some creams are water and oil emulsions. So a cream is an emulsion. So if it lost water, it will become dry. So this is not good to be used, cannot be used anymore. It's not soft, cannot be spreaded on the skin. Pastes also contain an amount of water. They will dry up upon storage if they lose water. Ointments, especially ointments having aqueous base, they may also lose some water. How to prevent loss of water from the several dosage forms? You can add a substance called humectant. Humectant is a substance that by nature absorbs water. So if it is a part of the formulation, it will absorb water, it will retain water within the formulation. Okay, so the definition of humectant is a hydrophilic substance added to the aqueous phase to absorb water from atmosphere and prevents its loss from the dosage forms. And examples of humectants is glycerin, propylene glycol can be used also. It's also a humectant. Okay, glycerin or propylene glycol. Sometimes the reverse can happen, that your dosage form, instead of having some water and then water will be lost to the environment, here it's supposed to be dry and it will absorb water from the environment. For example, powders. They may absorb water and liquefy and may degrade also, as we mentioned previously, that water can catalyze reactions. Reactions don't happen easily in a dry environment. If a solid form of the active ingredient, then degradation is very little. But if you dissolve the same ingredient in water, you put an aqueous medium, then it will degrade faster. Okay? So once they absorb water, then degradation may occur as a result of absorption of water. Hydrolysis reaction will happen. So they may degrade by mainly by hydrolysis. Okay, suppositories which made from hydrophilic substances like glycerine suppositories. It's not glycerine alone, but it is glycerinated gelatin actually. You have suppositories that are made from glycerinated gelatin. It mainly contains gelatin and contains a small proportion of glycerine. Glycerine, you know, is humectant and can absorb water from environment. Polyethylene glycol also is another type used to make suppositories. This is a base that can be used for making suppository base. So base means this is the excipient and active ingredient. And then suppository should contain a base plus the active pharmaceutical ingredient. Okay? So if the suppository base is made from polyethylene glycol and then you API is dissolved or dispersed in it or made from glycerinated gelatin, then it may absorb water and then may soften, become jelly-like appearance. And usually once we store them, they should be in a tight pack so that they don't absorb water from or humidity from the environment. Some of the other change in crystalline form, as it's supposed to be number one, we talk about physical instabilities. We give example of chloramphenicol. This is another example, cocoa butter. Cocoa butter is another suppository base. We use it to make suppositories. Cocoa butter is available in different different morphs. So it shows also polymorphism. It's available in different crystalline forms. And the problem in these different crystalline shapes or forms is the difference in melting point. So we need the form that is solid at room temperature or have high melting point. There is another form with low melting point. So if you change to this form, then suppository is easily melt. Okay. Chemical instability is that the drug will not be in the original chemical form. So if you have a drug, or we say API, for example, active pharmaceutical ingredient, it may have a degradation pathway. It may degrade and will form degradation products. Okay, so sometimes the concern is only the API. If degradation products are safe, they don't cause any toxicity, then I focus my attention on API. So the main problem for instability here will be the decrease in API content. Okay, if these degradation products are toxic, then there should be a limit for them. Their amount in the dosage form should not exceed this limit. Otherwise, they will cause toxicity to the patient that administer the dosage form. So sometimes the API is still within the range of up till more than or equal to 90%. Sometimes, for example, the content is 95%. This one's expected to be okay, still suitable to use, but at this amount, maybe you have a high level of degradation product that exceed the limit. Then this drug cannot be used anymore. This product cannot be used anymore. So the one that determines the shelf life, not only the content of active ingredient, but also the content of toxic degradation products. So shelf life here is the time that there will be significant change. It is the time required for significant change to happen. Significant change to happen can be chemical, can be physical. Maybe the active ingredient is below the limit. Maybe degradation products is above the limit. Maybe dissolution, physical characteristic like dissolution is below the limit and so on. Okay? So sometimes also the shelf life also, or the chemical stability is determined by degradation of an excipient responsible for product stability. As we mentioned in the previous slides, the preservative content. If the preservative, for example, this one's still okay, this one's still okay, but the preservative decreased to an amount that it cannot maintain the microbial stability anymore, then the product cannot be used anymore. This is the end of shelf life. Or also a degradation of emulsifying agents in case of emulsions, because if emulsifying agents degrade below a certain limit, then we will have physical separation of the two phases, the oil and water, right? So this will not be emulsion anymore. It will not be emulsion anymore. Maybe unpleasant color will occur, although still my active ingredient is okay, but sometimes only slight degradation causes a significant discoloration, change in color, that will not be acceptable to the consumer, like an adrenaline. Very slight change in adrenaline content, not acceptable to patients, pharmacists, or physicians, and the nurses. It will cause, there is a color change. Even still, the content of active ingredient is very high. It's not, there is no 10% loss yet. Okay? Then, when we talk about microbial stability, microbiological stability means, as I explained, I want to keep the sterility of dosage form or the microbial count within the accepted, keep the sterility or keep the microbial count within the accepted limits. Depends on the type of dosage form, whether it is sterile or non-sterile. Contamination from microorganisms is a big problem of formulations usually containing moisture. Okay, so this usually, if you have a dosage form that contains water, this is a suitable medium for growth of microorganisms. So in this case, I need to add preservative usually. This is not a problem in solid dosage forms. Usually, if I make tablets or capsules, for example, and they are isolated from, they are packed in good packaging that doesn't allow absorption of moisture, then they will not have microbial growth because they are dry. The environment is not suitable for growth of microorganisms. Okay? Microbial growth also can happen with some natural polymers used in the formulation. They themselves may be source of microorganisms. And the type of, so in case of pharmaceutical manufacturing, if I follow the GMP procedure, there should be a good control of the environment and good control of all the sources, not only the environment, all the sources that can introduce microorganisms to the product, so that I prevent microbial contamination of the formulations. What sources? What are these sources that can cause microbial contamination? Can be from the water used in manufacture, can be from the environment, from air, can be from the raw materials, from the containers and closures, from the personnel that are working in the company, in the production line, and from instruments and apparatus. That's why if you work in a pharmaceutical company, you will see that there is a quality control for water to ensure that it is, there are specifications it must meet, chemical specifications with regards to heavy metals, for example, chlorine and other ingredients, and that will come in the domestic water. So the domestic water usually in the company will have some water treatment unit. It will pass through first. And one of the treatments is that once passing through the tubes, there will be an area where there will be a UV light. Why UV light? So that I can kill the microorganisms. So this water will be clear of contaminants and microorganisms. When it comes to air, you know that there is air control, environmental control system, and they purify the air that is going inside. And you will study later on about what we call it HEPA filter. So there is a filtration system for the air supplied to the production plant. Raw materials, containers and closures, they should undergo all the tests to ensure that they are clean, they are free of microorganisms. If we use them to produce sterile products, then they should be sterile. There will be a sterilization step before using them to pack the material, the dosage form. Personnel, they should wear a protective garments of protective wear. So, you know, they wear overall, they wear gloves, they wear masks, and so on. Instruments and apparatuses, we have a clear cleaning procedures. Okay, we have a clear cleaning procedures to ensure they will not contaminate either with remainings from the previous batches, chemicals, or with microorganisms. Okay. Now we move to what factors may affecting the chemical stability of drug products. Okay. So the rate of degradation of drug products, the degradation itself is a chemical reaction, right? Degradation is a chemical reaction. So the temperature of storage, the pH of the formulation, exposure to light, the presence of moisture, the dielectric constant of the solvents, if there is any catalyst in the media, surfactants, they may affect the degradation, the type of dosage form, whether it is solid or liquid dosage form, and for semi-solid, for example, like ointments, whether they contain water or doesn't contain, and the ionic strength. Okay, these all factors that may affect the degradation of the drug should be studied, and then we should make the formulation in a form that can control these factors and lead to maximum stability of the drug products. Okay. First factor is the temperature. Usually, the higher the temperature, the faster the rate of reactions. Most of reactions, especially those are endothermic reactions, that they absorb heat when they happen, then the more you provide heat, the more will be the rate of reaction. So high temperature accelerates reactions that cause degradation of the active ingredient, like oxidation, reduction, and hydrolysis reactions, which lead to drug degradation. The rate of most chemical reactions increase with rise in temperature up to 2 to 3 times. Okay, can increase 2, 3, or 4 times even, with each 10 degrees rise in temperature. So this means that, for example, if your drug degradation rate, say 1 milligram per month at 20 degrees, if you increase the temperature of storage to 30 degrees, then the rate of degradation may be 2 times, means 2 grams, or 3 times, maybe 3 milligrams, sorry, not gram, milligrams per month. So the higher the temperature of storage of drugs, the shorter the shelf life. So what is the implication? The higher the temperature of storage, the shorter the shelf life. Why? Because the higher the rate of degradation. The rate of degradation. Okay. Mathematically, we have Arrhenius equation. that express the relationship between the temperature and the, do you remember this one? The reaction rate constant, right? The reaction rate constant. Usually, from last time, for example, you have first order reaction. So you measure the drug, say concentration or amount, change with time. If you draw a ln of this value, it's not the absolute amount, but you convert to ln, calculate the ln of the drug content, and then you plot versus time, you can get a straight line. Do you remember what we discussed in the previous lecture? And the slope of this line is K. The slope is K. This is the reaction rate constant, and this is a first order reaction. We say the rate of reaction is proportional to the drug content, drug amount. Rate of reaction is equal to K times the drug amount. Okay? So if you study two drugs and then one drug have a curve like this, A, and one drug have curve B, which one has a faster rate of reaction? I draw it clearly here, like this, and you have drug B, and you have drug A. Drug A. Which drug has a faster degradation, A or B? Can you answer me? A or B?
Drug A, Doctor.
Okay, why? Because the slope is higher, right? So
Yes,
this
Doctor.
slope is, so this slope is K. So the higher the K, we can conclude that means higher degradation rate. Higher degradation rate. Okay? So actually this is the exponent. Exponent here is inverse ln when you make it on the calculator. So this equation means that supposed to be ln K equal to ln A minus this amount. So this equation is ln K equal to ln A. When you get ln inverse ln, it is nothing. It's no ln at all. So minus activation energy divided by, this is not room temperature RT. R is the gas constant. Multiply by 1 divided by T. Okay? Is this a linear reaction equation or no? Here is y. 1 over T is x. EA over R is the slope. And this is the enter. Originally, the plot is ln K, we plot versus 1 divided by T, the inverse of the temperature. What temperature here? The temperature of storage. Okay? And then the equation that gives the relationship between K and T is as you see here. Mathematically, K equal to, we can write it like this, A divided by E to the power EA divided by RT, right? So if I take this one up, then it will be exponent of negative value. The power will be negative. But anyway, if you look at it mathematically, you will find that there is a proportional relationship between temperature and K. The higher the temperature, the higher the K. Okay, so I wrote it before as ln. But if you write it as log, then the conversion factor from ln to log is you have to divide by 2.303. So why this one is here? Because originally the calculations should be based on ln K versus time. But if you, because before they have only semi-log papers, so they can plot log K versus inverse of time. So in this case, once they want to calculate the slope, then they have to divide by the factor 2.303 to convert from log into ln. Okay, so in this equation, K is the elimination rate, the reaction rate constant. A, we call it Arrhenius factor, this one, the intercept. EA is called activation energy. This is different from reaction to another. R is constant. It has this value, 1.987 calories, degree to the power -1, mole to the power -1. It's constant. Temperature is the absolute temperature of the reaction medium or the storage temperature for your drug product. So it should be in degrees Celsius, say. Okay? So in Arrhenius equation to work, we plot, as we said, log K or ln K can. But if you plot ln K, then you should not use this fraction. Okay? This is a conversion factor from log to ln. Originally, calculation should be based on ln. So you plot, to explain this equation to you, I have to show you the curve. Okay. Let's say to explain to you, I have to draw the curve. Okay. You store the same formulation or same product at two different temperatures. Okay. And then you measure the drug amount at time intervals, say 1 day or 1 month, 2 months, up till 1 year, for example. Say up till 1 year, you follow. So 1 month up till 12 months. Up till 12 months. And then this one, for example, at 30 degrees, and this one at 40 degrees. Suppose 40 degrees will be, the reaction rate is faster, so the slope will be bigger. Okay. So it will be more steep, more steep, okay? So you calculate here the K at 30 degrees, and then you calculate the K at 40 degrees, K at 40 degrees. So now let's plot log K versus the inverse of the temperature. So at 30 degrees, K has certain value. At 40 degrees, 1 over 30 and 1 over 40 degree. So K has certain value. 1 over 40 should be here, of course, should be first time. And then this one should be 1 over 30. 1 over 30 degrees. 1 over 40 and 1 over 30 degrees. So here you have certain value for K, here you have certain value for K. Then you just draw the line. Okay? Do you remember in math? This line. The equation for this one is log K equal to, this is Y, log K is Y, equal to intercept and then multiplied by equal to log A, log the intercept, and then minus, because here it is decreasing, so the slope is minus the slope times x, 1 over t. And the slope is equal to EA divided by R multiplied by 2.303 because we use the log here. Okay. But now, how do I calculate the slope? You remember in math, we say the slope equal to, we take 2 points. This is x1, y1. This is x2, y2, right? The slope is y2 minus y1 divided by x2 minus x1, isn't it? So what is y2 minus y1? It is log k1 log k2 minus log k1, isn't it? In other words, you can write it as, log k2 divided by k1. It is same. Divided by x2 is 1 over temperature 2 minus 1 over temperature 1, right? So this is equal to the slope. What is the slope? The slope is activation energy divided by 2.303 times R. So actually this is, okay, let's move it. So this means that log K is equal to this amount multiplied by this. So this is the amount on the left side multiplied by this one. This one, if you want to form it, it should give you T2 minus T1 divided by T2 times T1. This is equal to this actually. This and this are equal values. Okay? This is where the equation came from. So this is from the slope equation. Okay, another factor that may affect the degradation of products is the light. So some drugs are light sensitive, some drugs no. We know that light itself has energy, and light energy will provide activation required for a reaction to occur. So, and absorption of radiation and energy to activate the molecules, independent of temperature for activation of the molecules. This is not related to the temperature of the medium. Only exposure to light while keeping the temperature stable may result in degradation of the drug. Okay? Absorption of one quantum of energy may increase the molecule's kinetic energy via collision, followed by a temperature rise. Attention to control wavelength and intensity here should be done. So, depends on your drug. If your drug is light sensitive, means the light can produce enough energy to degrade the product, then I should protect from the light of the wavelength and intensity that will cause degradation. So how to protect? We have to store them in amber bottles or opaque containers. So when you buy medicine, you see that some medications are in white or transparent glass or plastic. This means that they are not light sensitive, especially if you look at the vials and the ampoules of injections. Majority of ampoules are transparent. You see them transparent, automatically you should conclude that the drug is not light sensitive. That's why I don't need to protect. But some ampoules, you'll find that the color is amber yellow, dark. This means that they are photosensitive and they are packed in this kind of dark containers so that we can protect them from degradation by the effect of light. Is it clear up till here? Any questions so far? Okay. So now we move to the effect of solvent in case of liquid dosage forms. How does it affect the degradation of drug product? Drugs unstable in aqueous solutions may require incorporation of water, miscible solvents such as low molecular weight alcohols like polyethylene glycol to stabilize the drug. The addition of such co-solvent, we call it co-solvent in this case because it mixes with water. This can alter the activity coefficient of the reactant molecules and transition state, change the physicochemical parameters such as the pKa and viscosity to affect the reaction rate directly. Less polar solvents will slow reaction while more polar will speed the reaction. Okay. Okay. So water is a polar or non-polar solvent? Okay, there are two things here you need to know. Water is a polar solvent. Okay, and these substances are less polar compared to water. So if you mix them with water, they will reduce the polarity. Okay, what is the parameter that can determine the polarity of the substance? We call it dielectric constant. We call it dielectric constant. So if the dielectric constant is high, then the polarity will be higher. So now we can mix different solvents to make a mixture with certain polarity. We can reduce the polarity or we can increase the polarity of the solvent mixture by adding more water or by adding more less polar solvents. Okay. It's not in all conditions that less polarity will slow the reaction. It depends on the products, of the reaction. Okay. So dielectric constant of the solvents, this means the polarity of the solvent. It may affect the decomposition of the ingredient. Actually, we can say a better rule than what is written here. Here's, okay, if you have a reaction between ions of opposite sign, then when you increase the polarity of the solvent, it will decrease the rate constant, means decrease the rate of degradation. So it will decrease the rate of degradation. Okay, and if the reaction that will cause decomposition of the drug is between ions of like charge, then when you increase the dielectric constant, when you increase the polarity, you will increase the rate of reaction. There is another rule also. If the product polarity is higher than the reactant polarity, so product here is the degradation product. Reactant here is the drug itself. If the degradation product has higher polarity, then how to suppress the degradation? Make the opposite, reduce the polarity, reduce the polarity. So in this case, what to do? Then we have to, the action we need to do is reduce polarity of the solvent, then you stabilize the drug. How about if degradation product's polarity is less than the drug? So drug will decompose, will give less polar compounds, then increase the polarity. So in this case, action 2, suppress. You suppress the degradation. Okay. Also, some factors may catalyze the degradation of our drugs. These factors may be some specific catalysts, may be general, like acid-base catalysis, okay, like the effect of pH. So let's explain first what is catalyst. Catalyst is a substance that will influence the speed of reaction without itself being altered chemically. The catalyst generally increase the reaction rate by lowering the activation energy, which is the minimum energy required for the reaction. Catalyst is usually, once we just say catalyst, we mean positive catalyst, like in the definition here, will increase the reaction rate. But sometimes the catalyst can suppress, we call it negative catalyst in this case, if it will inhibit the reaction. Our problem is usually about the catalysts that will increase the degradation rate. And we can add some materials that will stabilize our drug to increase its stability, which is called as negative catalyst. So if we add negative catalyst, this is to stabilize, the action is to stabilize the product. Okay, so catalyst will increase the rate of reaction but will not affect the equilibrium. For example, if a drug will give a degradation product and the reaction is inverse and it will reach an equilibrium when the drug is, say, for example, 70% and degradation product is 30%. If you add catalyst, instead of reaching this equilibrium percentage in 2 days, you can reach it maybe in few hours. But the reaction will stop once the ratio is 70 to 30. So catalyst doesn't affect the equilibrium. Okay? And the yield is not changed. But it will just save time. It will when you do the reaction, you want to get some compounds, you are making reactions in industry to form certain compounds, then it will save time for you. But when it comes to degradation, it's not good because it will increase the degradation rate and reduce the shelf life. Okay. How catalysts work? It will may form a complex with the substrate, with the drug, and then this complex will decompose to regenerate the catalyst and yield the product. As we mentioned, it works by decreasing the energy of activation. This may be by changing the mechanism of the reaction. They usually produce free radicals like CH3. This is a free radical. It is very reactive and then can start a chain reaction. Okay, it can react with other materials and initiate the reaction. Catalysts may be homogeneous or heterogeneous. Homogeneous if they are same phase like the reactants. For example, it is liquid substance mixed to reactants in liquid state, or gas mixed to reactants in gaseous state. Then we're talking about homogeneous catalysis. And maybe heterogeneous catalysis, like, for example, when you do reaction between gases and the catalyst is solid, metal catalyst, for example, solid, in gas or liquid phase, then this is a heterogeneous catalysis. Addition of acids or bases, it may accelerate drug decomposition. This is accelerated decomposition is found to contain a term involving the concentration hydrogen or hydroxyl ion. So in this case, addition of acid or base can affect such reactions that the reaction have reaction with hydrogen or hydroxyl ions. Okay, Hydrogen ion concentration indicates that the process has a specific hydrogen ion catalyzed reaction in the reaction. So examples, we may do acid hydrolysis or alkaline hydrolysis. So you may hydrolyze your compound by acid hydrolysis, means that the hydrolysis reaction will be catalyzed in presence of acids. And there is alkaline hydrolysis, means that you add alkali, then you speed up the hydrolysis of your compound by the alkaline alkaline medium. Some drugs may have significant alkaline hydrolysis, will be hydrolyzed more in alkaline pH. Some drugs may be hydrolyzed more in acidic pH. So you have to do a study and study the degradation of the drug at different pHs. And then the formulation should have an optimum pH that result in minimum degradation of the drug. How to maintain this pH? We can maintain the pH by the use of buffers. So you study buffer solution, how to make it. It's usually a mixture of acid and its salt. For example, acetic acid and sodium acetate, or base and its salt, for example, sodium hydroxide and say sodium chloride, for example. Okay, so in this case we have or maybe say NH4OH, the ammonia, and say ammonium chloride, NH4Cl. Okay, so this is a buffer. Usually we adjust the amount of acid and salt to achieve certain pH. There is a certain way to calculate the amounts required to achieve certain pH. Okay, so actually we explained this one in the previous lecture. I'm not going to repeat it again, but we mentioned about that most of the drugs are stable between pH 4 and 8. And then we have to study the ionization of, we know that the ionized form of the drug is the one that is prone to degradation. So we have to choose a pH that suppresses the ionization of our drug. But the problem is when the drug is not ionized, it is less soluble. So we have to choose an optimum pH that will achieve a certain degree of solubility and suppress ionization. This may not be possible because if you ionize, it will degrade. So instead of adjusting the pH to increase the solubility, I can use a co-solvent, water-miscible co-solvent, that will improve the solubility of the drug, and I don't need to increase the solubility by increasing ionization. We gave examples last time. We said alcohol, propylene glycol, alcohol like ethanol or propylene glycol can be used as, or glycerol or glycerine can be added as a co-solvent. It will increase the solubility and suppress ionization at the same time. Okay? We gave example last time. So how to study? We usually have different test tubes with different pH values. So say pH 1, pH 2, pH 3, and then I study the degradation rate, means I determine the concentration of drug in each of them. And you have concentration over time for pH 1, for pH 2, pH 3, and so on. I determine the K for each of them, and then I can plot the log K versus the pH. I see the change in K with pH. So it may have this shape, it may have this shape, whatever. And then I choose the pH with the best stability, the least degradation rate. Okay? So this is what we call it a pH decomposition profile. Moisture, as we know, moisture can catalyze chemical reactions, and can also promote microbial growth. So it affects chemical stability and affects microbial stability. If it will lead to liquefaction of the solid, then also affects physical stability. Oxygen, it may cause oxidation of drugs sensitive for oxidation, and then it will result in degradation. So it all, whether I need to control this factor or no, depends on my study of my drug. If I find that drug is easily oxidized, then I can protect from degradation by adding antioxidants to the formulation. In pharmaceutical dosage forms, we said liquid is usually less stable compared to solid, as we mentioned. Because of the presence of water will accelerate degradation. So solid dosage forms are more stable. So you may see that for certain drug, the tablet shelf life is maybe 5 years, but the serum of the same drug has a shelf life only of 2 years. This is because rapid or faster degradation happens in aqueous environment. Drug incompatibility also may affect the stability of the drug. Drug incompatibility may be with other drugs, drug-drug incompatibility, and maybe with the packaging, and maybe with the excipients. So in the formulation, the formulation may have more than one drug, maybe a combination containing, for example, paracetamol and antihistamine or decongestant. They may react with each other, and they cause degradation of each other. Or they form, not degradation, maybe they form reactant, so there will be consumption of the active ingredient itself. Okay, so the content of active ingredient will decrease. And drug may react with the other excipients, or some excipients may increase the degradation rate of the drug, and may also interact with the packaging material. So this may affect the drug stability. This is an example of acid catalyzed hydrolysis reaction, digoxin. Digoxin actually may be hydrolyzed, and this hydrolysis is catalyzed by acid. And this follows pseudo first order reaction. Okay? So it follows the first order reaction, means that the degradation rate is proportional to one factor only. Okay, and the power is 1. One factor, the power is 1. However, this is pseudo. Why pseudo? Because actually there is reaction between the digoxin and acid. Okay? So in this case, the rate of reaction is supposed to be proportional to the product of the drug content and the acid content. So this is second order reaction, according to the law of mass action that we explained last time. However, the value of H is stable, remains constant. So since it remains constant, doesn't change with time, the only factor that changes with time is the amount of digoxin. So the reaction rate will be dependent on the digoxin amount. So that's why it is pseudo first order. It goes first order, but not because in the reaction there is only one term, which is the digoxin amount. No, there are two terms, but only this is the one that changes with time. Okay. Hydrolysis of chlorbutanol in presence of sodium hydroxide. So chlorbutanol plus sodium hydroxide gives some reactant. So reaction rate is proportional to the product of chlorbutanol times the sodium hydroxide. So this is a second order reaction, and it's real, not pseudo first order, because both of them, the concentration change with time. Okay, now we go to the determination of expiry date. Expiry date means the time that the drug performance is not accepted anymore. It's outside the accepted limits. So this, and then we cannot use the drug beyond this expiry date. So expiry date means that the drug cannot be used after this date because the concentration of the drug is decreased and becomes lower than therapeutic concentration. Or we may have some degradation products that increase above the limit, or we may have some low performance in other physical tests like the solution test, or preservative concentration may decrease, and so on, the things that we mentioned before. This is related to the shelf life or use with storage. When we talk about storage, then we talk about expiry date. How about in-use stability? So we follow the expiry date when it comes to if the container is still closed, we didn't open, but after we open, different rules applies. Why? Because there may be some microbial contamination, there may be some degradation by exposure to the environment and so on. So mainly because of microbial instability, there is a different rule applies after we open the container. If we open eye drops, we can use it within 1 month only after opening. Even the expiry date still valid. Even we didn't reach the expiry date yet, but we should follow this rule. For syrups and suspensions of antibiotics, here because of not microbial really, but because of chemical stability. You know the antibiotics, they don't come as ready-made, but they come as powder. And just before use, you add water, right? So before they are in powder form, so powder is stable. The shelf life is calculated for the powder form. So they can be stable, say, for 3 years. So anytime within 3 years, still the powder is having the required characteristics, the potency is okay. But once you add water, then degradation will accelerate, right? So they cannot be used, they cannot be stable for a long time once water is added. That's why we store them as powder. Why we store them as powder? Because if you added water, they cannot remain stable. We just add water before use, but once you add water, then should consume within 2 weeks. Okay? If you keep them in the fridge, and 1 week if you keep them outside the fridge. Of course, the lower the temperature, the less the rate of degradation, the longer the shelf life. For tablets and capsule, after removal from the package, may change. Usually we don't remove them unless we use anyway, so it's not an issue in tablets and capsules in general. For ampoules, must be used immediately in case of ampoules because they are sterile and they don't contain preservative. Once you expose to the environment, then they may be contaminated and there will be microbial growth. For vials, there are single dose vials and there are multiple dose vials. Multi-dose vials, for example, like insulin or like vaccines that will be given to 100 people, for example. Insulin you can use for 1 month, whatever. For this one, we take dose today, we take another dose tomorrow and so on. They should contain preservative. So they should be used, they can be used within the written period. Just follow, not necessarily 24 hours, because like insulin you can use for the whole month, there is no issue because there is preservative, okay? But if it is ampoule, then it cannot be stored. You use the amount you use, the remaining should be discarded. For ampoules, for example, the ampoule containing 5 ml, and we need to take a dose of 2 ml only. Once you open the ampoule, if you will not give the remaining to another patient immediately, you cannot keep. You should discard the excess. Okay, now we go to the an important part, which is stability testing. How we do the stability testing? There are different types of stability testing. There is stress testing and there is accelerated stability and real-time stability or long-term stability. So we have stress testing and we have accelerated. This is another term, another form different from this one. We call it accelerated stability. And we have long-term stability. Long-term stability, we store the drug at the storage temperature. At the storage temperature that will be used during marketing. For example, if it's supposed to be kept at room temperature, then we keep at room temperature. Okay? And then we study the rate of degradation. Accelerated stability, we keep at higher temperature. At higher temperature. Stress testing also at higher temperature and much higher. This accelerated and long term, we need to calculate the shelf life. We use it to calculate the shelf life. What is the purpose of increasing temperature? You increase the temperature so that you increase the degradation study. So I do stress testing because I want to get quick results. I want quick results. So I increase the temperature so that I can study the degradation faster. I can get degradation products in higher amounts and I can study them. So stress testing is a research tool to discover potential stability issues with drug molecules. So in this case, I can, for example, see how fast the degradation of drug. What are the degradation products? I can identify them, identify the likely degradation products of drug substance. I store at 60 degrees or 70 degrees, and then I analyze and I separate the degradation products and identify their structure and so on. I can also predict the drug excipient compatibility by making mixtures of drug and excipient. I make mixture of drug. I use, for example, in the tablet, I will put lactose and I will put microcrystalline cellulose. So I put drug and lactose alone, and I put drug and microcrystalline cellulose alone. I keep at 70 degrees, and then I study the degradation rate of drug in this mixture, mixture 1, and the degradation rate of drug in mixture 2. And the one that gives less degradation is more suitable to use with the drug. Okay. I can also use it to develop stability indicating analytical method. I want to develop analytical method like HPLC method that should be able to identify the drug in presence of degradation products. How can I test this? I have to produce degradation products. How? I can store the drug at higher temperature to produce degradation product and then analyze the drug in presence of degradation products. I see if it is really separated or no. I can also use alkaline hydrolysis. This is what we call it force of degradation. Force of degradation can be by temperature, by pH. I can add acids, strong alkalis, which also will increase the degradation of the drug product. Then I test the analytical method. And also I can add oxidizing agent. For example, hydrogen peroxide or iodine, okay? I can add them to the drug and see the degradation. When I can do this stress testing for active pharmaceutical ingredient for the drug substance, and I can do also for the formulation during formulation development to perform drug excipient compatibility studies. Actually, here it is written comparability in this source, but we use more the term compatibility with T. Okay. So for stress testing of API, I can use stability indicating method that can determine the drug in presence of a degradation product. I call it discriminating method. And here I can separate degradation product and identify them. And I can determine, I can do accelerated testing to determine, here I just talk about identification. So I talk about qualitative. When I do accelerated testing, then I want to determine the amounts and see which one in bigger amount. And after this, I can monitor over long-term testing. Long-term testing, this one is done at the storage, the intended storage temperature, at the intended storage temperature. This is the long-term testing or real-time testing. I can do for formulation development, as I explained to you, and I can just do for mixture of drug with separate excipients individually, and then with the final formulation, and it can give me idea about the compatibility of drug with these ingredients. I usually make it at higher temperatures than the storage temperature. I can do at 50, 60, and 60 degrees with high humidity, 75% or greater. I can add, as I told you, oxidizing agent, acid, base. I can expose the drug to light to study if it is the photolysis, if it is light sensitive or not. Okay, so the testing should also evaluate susceptibility of the drug substance to hydrolysis across a wide range of pH, as I explained, when in solution or suspension. Okay, now we go to accelerated stability study. They are designed to increase the rate of chemical degradation or physical change of a drug substance or drug product by using exaggerated storage conditions as part of the formal stability studies. So now when we talk about stress testing, this is just to get initial rapid results, but it's not the one to determine the shelf life. When we say stability study, then we want to determine the shelf life. So the aim of stability study is determination of the product shelf life. We will study the rate of degradation, and then we can determine the time period where the content of the drug will not fall below the accepted limit. Okay, so there are two types, as I told you, long-term and accelerated. Accelerated is initial results. We can get initial results about the degradation, but we cannot use it to actually. Previously, they used the methodology I explained now for calculation of for expectation of the shelf life at the room temperature, but this is not yet acceptable by regulatory authorities to determine the final shelf life. It's just a preliminary estimate. Okay, so what we do in accelerated stability study, we have to store under exaggerated storage conditions. So suppose that room temperature is 30 degrees, then in accelerated study, I will study at 40 degrees and maybe also at 50 and 60 degrees. Okay. So here we have faster degradation rate. So it can help us to do the study at a shorter time. And the data from this one, in addition to the long-term stability studies, can be used to assess long-term chemical effects of at non-accelerated conditions. How? I will explain to you. But usually, as I told you, results are not always predictive of what will happen at room temperature, whether physical or chemical changes. It's just a preliminary estimate. And this is done in early development on pure drug to assess the stability and identify degradation products. Can be done also to the dosage form to help define the limits and critical parameters that impact stability. May be used to extrapolate or estimate the shelf life at room temperature, as I will explain in the coming slides. And we said that we extrapolate. How? We do at higher temperatures than room temperature. So if the product is supposed to be kept at 30 degrees, for example, I can store the drug at different temperatures, higher temperature, 40, 50, 60, and 70. And then I study at different time intervals after, say, for example, 1 month, 2 months, 3 months, 4 months, 5 months, and 6 months after the start of storage. I can determine the concentration of drug at these time intervals at different time temperature. So I have separate curve for each temperature. So if I plot concentration, supposed to be log or long concentration versus time, then I get different curves and then I get different slope, right? So higher slope means higher degradation rate, and small slope means slower degradation rate. I get K at 70 degrees, K at 60 degrees, the K at 50 and K at 40 degrees. Then I plot log K versus 1 over T, the one we explained previously about Arrhenius equation. Then you extend the line. So the data here taken from this curve is only up till 40 degrees. So this is the last point, the real point. So I plot and then I extend the curve. I extrapolate. This is the extrapolation. I extend the curve. So I determine then what is the value of log K at different temperatures. I can I can extrapolate. I can get the value of K at 30, 25, and 20. This may happen in reality, may not. It's not predictive 100%. Okay, so in Europe, the room temperature is 25. In Malaysia, the room temperature is 30 degrees. So if I'm doing the stability study in Malaysia, I want to determine K 30 degrees, and then from it I can estimate the time for 90% purity. Okay, the time for the drug to decrease from 100% to 90%, which determines the shelf life. Okay, but when we do accelerating stability study, we should have the same components in the final formulation. You cannot do study on certain formulation and expect it will give you the shelf life for a different formulation. Okay. The method you use for determination of the amount or the concentration of drug should be stability indicating. Means that no interference from degradation products. It can determine the amount of drug accurately in a complex mixture containing excipients and containing degradation products. And we may use statistical analysis in this one. How do we estimate? I can use the Q10 method. Q10 method, I can calculate the time required for 10% of the drug to degrade and 90% remain intact from the drug. Okay? So, if it is a first order reaction, the time is equal to 2.303 divided by K times log initial concentration divided by the second acceptable concentration. Okay, so in this example, let's solve an initial concentration of drug decomposing according to first order kinetics is, according to first order kinetics is 94 units per mil. The specific decomposition rate K obtained from an Arrhenius plot is 2.3. This is K at the storage temperature. If we want to estimate shelf life at 30 degrees, then it should be K30. This is the value of K. Here K is at 25 degrees. The acceptable, it's considered expired if we reach 25 units. Below 25 is expired. So I want to calculate the time from 94 up till 45. Okay, so I will apply in this equation the time to decrease from 94 to 45. I just put here the 2.3. I replace K with the value given. And then here the initial concentration, here the final concentration. So I can apply it for 90 and 100%. So C0 I can put 100. If expired when reach below 90%, then C is 90. And then I apply the value of K at 25 degrees, or if I'm doing the study in Malaysia, then at 30 degrees, how much is K? I substitute the value of K. And then I will get a time interval. The units of that time is same like the unit on K. So K here is hour to the power -1. So it must be, the time calculated is in hours. And then I convert into years. So here I get the shelf life is 4 years. Okay, so if you have this one for decrease from 94 to 45, but regulatory bodies usually for most drugs, they use the 90% as the expiry point. Okay, this is the use of the time according to first order reaction if my drug degradation is a first order degradation. So there's another method, we call it Q10. Q10 is the ratio between the K values at two temperatures. One of them is 10 degrees high. This is used to estimate the effect of 10 degrees rise in temperature on the stability of pharmaceuticals. Q10 is the factor by which the rate constant increase for 10 degrees Celsius temperature increase. So Q10 is, for example, the K at 40 degrees divided by the K at 30 degrees Celsius. Or for example, if it is the K, the degradation rate constant at 50 degrees divided by degradation rate constant at 40 degrees. The difference between them is 10 degrees. Q10 actually is, the Q value can be 2, can be 3 times, can be 4 times increase in the value of K, depending on the activation energy. The higher the activation energy, and then the higher the increase in the K value. Okay? There is an equation for K10. It is the exponent of activation energy divided by gas constant multiplied by the higher inverse of the higher temperature minus the lower temperature. Where did we get this one from? We get this one from the plot of K versus 1 over time. Ln K versus 1 over time. Okay? So Q10 is equal to, if we have K1 and K2. Okay? So Q10 is K with the higher temperature. So this is K2 actually. And this is K1. Okay? So it is equal to this divided by this. If you modify the previous equation, then you will get it. We said the slope is, K is the slope. K here is not the slope, sorry. K here is not the slope. So this is K2 divided by K1. So look at the equation. Y is ln K equal to ln A minus activation energy divided by R times this one. So you divide ln K1 divided by, so you convert it to K, so you get the inverse ln. So inverse ln equal to A minus, you remove the ln here, and this one will become exponent to the power negative this one divided by T. So K divided by Ka will be omitted, and then you will get K1 and K2, T1 and T2. Okay? Instead of Q10, we have also Q maybe 20. If the difference is 20 degrees, this equal to K, say for example, T plus 20 divided by K, T. For example, you can say K 40 degrees divided by K 20 degrees. Reaction rate constant at 40 and reaction rate constant at 20 degrees. Any two temperatures that the difference between them is 20. Okay, this is also equal to, we can calculate it from, if you want to expect the ratio between the K values with certain increase in temperature that is above 10 or below 10 degrees. So this is equal to Q10 to the power, the difference in time. For example, if you are talking about Q20, if 20 degrees, then 20 divided by 10. Okay? Then how to calculate from Q10? If you know the Q10, then T10 at certain temperature equal to T90 at certain temperature is the time to reach to 90% of the content at temperature 1 divided by Q10 to the power delta T divided by 10. So say, for example, you know the Q10 value, and you know the time for degradation at 40 degrees. you want to calculate the time for degradation to 90%, say at 30 degrees. So how to calculate it? You substitute the time for degradation up to 90%, means degradation of 10% of the drug, at the 40 degrees divided by the Q10 value to the power. What is the difference between 40 and 30? The difference between them is 10 degrees, right? So to the power 10 divided by 10 means to the power 1. This is cancelled, the power 1. So it is divided by Q10. If from 50 degrees, you have the data about degradation at 50 degrees, and you know the time for decrease of content till 90% at 50 degrees. You want to calculate at 30 degrees, then you substitute the one at 50 degrees. But here the difference between 50 and 30 is 20. So Q10 to the power 20 divided by 10. So Q10 square, 20 divided by 10 is 2. So divided by Q10 square. Okay. Now we go to packaging and stability. Is there any effect for packaging material on stability? Yes, we have different materials have different nature. So maybe I'll discuss this one, and then I will need actually 1 hour more to finish this topic. Okay. Packaging of the drug product is very important when stability is being considered. The immediate container and closure are particularly important in affecting drug product. What do we mean by immediate container? Immediate container is the container that comes in contact with the product. So for example, you have a syrup in a bottle, and this bottle is in carton box. The immediate container is only the bottle and the closure, not all the closure, the inside part of the closure that come in contact with the drug. This one we call it immediate container. But this one, the outer box is not immediate. Outer box is not immediate container. So the container, the parts of container or packaging material that will come in contact with the formulation or the drug product is the one that may interact with it. We may use glass, we may use plastic, we may have rubber, especially the stopper. The stopper may be rubber. It may be metal also, the stopper, or maybe some bottles may be metal, like in case of inhalers. So this may interact with the drug. Okay, what kind of interaction happens? We have different interactions based on the type of material. I think enough for now. We can stop by this part. Then we can have 1 hour more for the remaining part of the lecture. Okay. Any questions so far?